To study action potentials, we need to record the activity of a neuron. To do so, we use the patch clamp technique that is described in a supplement. Here the neuron is a round cell. Its activity is recorded in whole cell configuration to record the activity of the whole membrane, and in current clamp mode to record changes of potential of the membrane. We apply a current step here through the electrode, and we record through the same electrode, we record the response, which is a small depolarization of the membrane. Now, if we increase the amplitude of the current step, what will be the response of the membrane? You have here on the right the increase of the current intensity injected in the neuron, and you have in green the response of the neuron. What you can see is that the response is proportional to the amplitude of the current step. We say that the response of the membrane is linear. Now, if we go on increasing the current step, increasing its amplitude, what do we get? You see here that we get a very different response, which is sudden, short. Here you have the time scale. It's around 1 millisecond of duration. This response is what we call an action potential. It's all or none. What does it mean, all or none? It means that it has an amplitude which will be constant whatever whenever we do. If we increase more and more here the intensity of the current step, this response here will not change. So all or none, it means that either it exists or it does not. And there is a threshold potential because it appears from a certain depolarization, which is here. Below this potential of around minus 50 millivolts, there is no action potential, but just after there is an action potential. So it's a response that has a threshold. Let's revisit the properties of the action potential. From a certain threshold, a depolarization threshold, there is a depolarization phase here, followed by a repolarization phase. What does it mean? It means that from the threshold, the potential of the membrane becomes less and less negative and even reverses and then comes back to the basal potential. This is the simplest explanation. So this is done by ions because everything is due to ions in neurons. So let's test which ions are involved. First, we apply a blocker of potassium channels. This blocker is called tetraethylammonium, TEA, and when it's applied in the bath, in the recording bath, you can see that the depolarizing phase is nearly the same, but the repolarizing phase here is much, much longer. And this repolarization is affected by the blockade of potassium channels. Now, if we add on the top of the channel blocker, the potassium channel blocker, if we add also a sodium channel blocker, which is here TTX, tetrodotoxin, you see that the action potential has completely disappeared and there is only, this passive response that we saw before. This suggests that potassium ions and sodium ions are involved in action potentials. But are they the only ions involved in the action potential? To test this, we add calcium channel blockers, and we see that there is no change of the amplitude or the duration of the action potential. And the same, for example, we can use a recording bath devoid of calcium ions, and also there is no change of the action potential. Now, let's test the chloride ions. If we add chloride channel blocker, or if we replace extracellular chloride ions with non-permanent anions, there is no change. So all this means that calcium and chloride ions are not involved in the sodium action potential. Then we have the following hypothesis. Potassium ions participate in the repolarization phase because we saw that when we added potassium channel blocker, we increase the duration of the repolarization. And sodium ions, we don't know exactly. Either they participate in the depolarizing phase only, or they participate in both. We don't know. So to test that, we have to record the ionic currents underlying the action potential. To record the currents that underlie the action potential, we record the activity of the neuron in whole cell configuration, to record the activity of the whole membrane, and in voltage clamp mode, to record the current, the total current that crosses the whole surface of the membrane. So we record here current versus time. First, we hold the membrane potential at minus 80 millivolt. When the membrane is hyperpolarized at minus 80 millivolt, there is no change of current recorded. The membrane current is stable. Then we apply here a depolarizing step through the electrode, and we record a sudden inward current followed by an outward current. So here it's inward. I remind you that an inward current is an entry of plus charges, and here an outward current, which is an exit of plus charges. These two currents, what are they exactly? To understand this, we apply the same blockers that we did previously. So first, the tetrodotoxin, which is a blocker of sodium channel, and we see here that the inward current had totally disappeared. There is only the outward current. This means, suggests strongly, that the inward current is in fact a sodium current. Now, let's test the reverse. We apply only tetraethylammonium, the blocker of potassium channels, and we record only the inward current. The outward current had disappeared. This inward current is larger. This is normal. We will explain why later. So we can suggest here that the inward current is a sodium current and the outward current is a potassium current. We now know that the sodium current is responsible for the depolarization phase of the action potential, and the potassium current is responsible for the repolarization phase. Why? For example, for the sodium current, sodium ions enter the cell. When plus charges enter the cell, the inner face of the membrane becomes less negative compared to the outer face. This is a depolarization. When there is a potassium current, potassium ions exit, leave the cells. Therefore, the inner side of the membrane loses plus charges. This is called a repolarization because the membrane was previously depolarized and now it's going to return to its previous basal value. It's called repolarization. Looking at this recording, we can ask a number of questions. First, why is the sodium current the first to appear? And it appears from a certain threshold. If the depolarization here was not so high, we would have nothing. So why does it appear first from a certain threshold? Why is it so fast, so short? And why is it inward? Then, for the potassium current here, why is it delayed? And why is it outward and longer? To address these questions, we have to record the unitary current, so the current through single channels, and we will begin by the sodium current.